right, in this video, we're going to take a look at antiderivatives. So we're basically going to learn all of our derivative rules that we've talked about up to this point in reverse. So suppose I have f prime equal to x squared, and I'm wondering, well, what was the original function that I used to get that derivative? Now, we know that this is a second degree polynomial, which according to the power rule says that we should have started with a third degree polynomial. That's how the power rule works. You subtract a 1 from that exponent, and your original goes out front. So a good guess might be x cubed. Now, if I want to make sure that this is the correct answer, I can take the derivative. For any antiderivative, you can always take the derivative, and that'll be the best way to check your answer. As long as you get the thing you started with, then that is the correct antiderivative. So let's take the derivative of x cubed. Well, I get 3x squared, but I'm supposed to have 1x squared. So I want to maybe doctor it in such a way to where that 3 coefficient will cancel off with something else. So maybe if I use instead x cubed all divided by 3, then when I take the derivative, the 3's will cancel, and I'll have 3 over 3x squared, which is the same as x squared. All right, that works. So something else that could have worked, since the derivative of any constant is 0, I could have also chosen x cubed over 3 plus 6, or plus 10, or plus 100, or for that matter, plus any constant. So when we're finding our antiderivatives, we're always going to have to write a plus c, unless we have a certain set of scenarios that we'll talk about a little bit later. But for now, we're always going to have a plus c, and the reason for that is because the derivative of any constant is 0. So this is actually our first rule for antiderivatives. This is our power rule for finding antiderivatives. So if I have a derivative equal to x to the n, where n is not -1, so this works for every other rational power, then my antiderivative, or the function I must have started with, to find that, I add a 1 to my exponent, and then I take that result and then divide by that result. So if you go back and look, I started with x squared. If I add a 1 to that 2, I get 3, and then divide the whole thing by 3, and that comes up with the correct antiderivative. So there's going to be some notation that's a little bit different this unit, and it's going to look like this. So instead of saying f prime equals something, find f, we're going to write it with this elongated s looking thing with a function and then a dx, and then we're going to hopefully find what f of x is and always attach that plus c. This is called an indefinite integral. We're going to talk about definite integrals later on in this unit, but for now, they're all going to be indefinite, which means we always have that plus c for the same reason of derivatives of constants are 0. So each part kind of has a name. That elongated s thing, that's an integral symbol. The function on the inside that we're trying to find the antiderivative of, that is an integrand with a d at the end. And then the thing on the right, our answer, is going to be the antiderivative. So we could write that power rule in integral form, which would look like the integral of x to the n dx equals x to the n plus 1 over n plus 1 plus c. Now you're probably wondering, what's the deal with that dx? Well, we need to know what the derivative was taken with respect to which variable. If you remember that implicit differentiation, like the dy dx, dr dt, all of that stuff, we need to know what derivative we took with respect to, or I should say which variable we differentiated with respect to. So there's always going to need to be a d something there. So if you look at this rule, this is our first antiderivative rule. Think about the derivatives of other functions like sine, cosine, tangent. Take a second and pause the video and try to imagine or work out, if you can, some integral rules or antiderivative rules for sine and cosine and something else. So take a second, pause that, and then in 3, 2, 1, I'm going to show you the integral of sine of x dx, or the antiderivative, is going to be minus cosine x plus c. You might be wondering, what's the deal with the negative? Well, again, you can always take the derivative to check your answer. The derivative of cosine is minus sine, so minus minus makes plus. I'm supposed to always end up with the integrand, the thing on the inside of my integral, when I'm checking my answer. You could probably guess what the integral of cosine x dx is going to be. That's going to be sine of x plus c. You could take the derivative and check. And then another one, if I'm looking at the integral of secant squared x, that's going to give me tan x plus c. Same reason. Now, there are a couple others I'm not putting up here. You can Google them or look them up in your book, but these are the main ones that we're going to focus on in the near future. That should do it for now, and you should be able to answer all of those questions on Schoology.